we are discussing the design of CPU, and in last class we have read the design of one type of control unit called the hardware control unit. Today we will read the other one, the microprogrammed control unit. So, first we see what do we mean by microprogrammed control unit, and then we will read the design of that particular type of control unit. Now, microprogrammed control unit contains the programs, and this program is nothing but a set of micro instructions. Now, programs are stored in a control memory, normally in a ROM inside the CPU. Now, to execute instructions, the microprocessor first fetch each instruction into instruction registers from external memory. Then the control unit translates the instruction. Each control word contains signals to activate one or more micro instruction. After translating this instruction, then the control unit decides or activates the control signal that what particular operations to be executed. Now, a program consisting of a set of micro instructions is executed in a sequence of micro operations to complete the instruction execution. As this microprogram is nothing but a set of micro instructions, so it is very much important that what will be the format of this micro instruction, so that this sequence of micro operations or micro instructions to be read to control the micro operations. Now, all micro instructions have two fields, one is control word, another is next address. Now, this control word indicates which control lines are to be activated, and next address specifies the address of the next micro instruction to be executed. Now, the memory which contains this microprogram, we call this is control memory. Now, we see what will be the features of this control memory, or how actually the control memory is being accessed, or how it is written data onto it. Now, the concept of microprogramming was first proposed by W.V. Wilkes in 1951. So, when first it was introduced, the microprogram utilized a decoder and a 8x8 ROM with a diode matrix. So, that was the first implementation of a control memory. The two components are a decoder, one decoder and an 8x8 ROM with a diode matrix. Now, this same concept is extended to include a control memory inside the CPU. So, now the control memory stays inside the CPU. So, the cost of a CPU primarily depends on the cost of the control memory. Now, the length of a micro instruction affects the size of the control memory. Therefore, a major design effort is to minimize the cost of implementing a microprogram CPU by reducing the length of micro instruction. As the length of micro instruction affects the size of control memory, and the control memory, cost of control memory decides the costs of CPU. So, first effort is to reduce the length of the micro instruction. So, it will reduce the cost of memory, and finally, it results the reduction of the cost of CPU. Now, to minimize the cost of implementing a microprogram CPU, reducing the length of micro instruction is needed. Now, the length of micro instruction is directly related to the number of micro operations that can be activated simultaneously, called the degree of parallelism. As the program is a set of instructions or micro operations, so in every program there are some of the micro operations can be performed simultaneously, and as it is performed simultaneously, we call that these are some parallel of micro operations. This is some degree of parallelism. So, the length of micro instruction directly related to this degree of parallelism. Another thing is the method by which the address of the next micro instruction is determined. So, mainly these two features, the number of micro operations and the method by which the address is decoded, these two determines the length of micro instruction. So, we see what will be the design of micro instruction first, because this is the primitive of the micro program. Set of micro instruction is a micro program. Now, all micro instructions executed in parallel can be included in a single micro instruction. This is very important thing, that means say parallelism is exploited to reduce the number of micro instruction. So, the micro instructions which executed in parallel, they are included in a single micro instruction with a common opcode, and this results a short micro program. This results a short micro program. But the length of micro instruction increases as the parallelism grows. So, number decreases, but the length increases. So, here what we can tell that for the effect of parallelism is it reduces the number of micro instructions. All the micro instructions that are executed parallelly, they can be combined to a common opcode, and that means it is a one single micro instruction. Obviously, that is much shorter if we consider all the micro instructions that are combined, but parallelly it increases the length. Obviously, as a number of operations are combined, so though it now it gets a common opcode, but the length of micro instruction is increased. So, we need a optimization, that what degree of parallelism can be considered, so that the reduction of micro instruction or the increase of length of micro instruction can be optimized. Now, full parallelism can be achieved by assigning a single control bit for each control line. The control bits in a micro instruction can be organized in several ways, and one obvious way is to assign a single bit for each control bit line, and this will provide full parallelism. So, no decoding of the control field is necessary. Normally, this organization is of two types. One is called the encoded format, another is unencoded format. Now, we consider one example of a register transfer and we see that how this control bit organization can be achieved. See, here there are two registers, X and Y, X, Y, two registers and one out bus, Now, C0 and C1 are the control bits. So, if C0 equal to 1, X is or out bus is X, out bus gets the content of register X. If C1 equal to 1, then out bus gets the contents of register Y. So, this is the register transfer. Now, here each operation can be performed one at a time, because there is only one out bus. So, a single bit can be assigned to perform each transfer in this way. Say, first we consider the unencoded format. Unencoded format, so this is the normal a simple situation that when each control bit is 1, one operation is performed. So, C0 is 1, X is assigned to out bus or the content of this register goes to the out bus. If C1 is 1, content of Y register goes to the out bus. If all are 0, C0, C1 is 0, there will be no operation. So, these three operations can be done by specifying the control bits C0, C1 as 10, 01 and 00. Now, the same thing can be done in different way in a encoded format. See, as it is encoded format, so here the relationship are like that. Say these are some bits D1, D0. Say if we consider these three operations we implement using 2 bits and a 2 to 4 decoder. So, as if D1, D0 are the inputs of this decoder. Now, if D1, D0 is 0, 1, X contents of X goes to out bus. If it is 1, 0, contents of Y goes to out bus. If it is 0, 0, then there is no operation. So, unencoded format, these were the control bits and now these are the inputs of a decoder. So, here this encoded format can be implemented using 2 bits and 2 to 4 decoder. So, encoded format provides a short control field. Why? See, if we have some 5 control lines, then we need a 3 to 8 decoder. 5 control lines, then for unencoded format, say for unencoded format, we need 5 bits C0, C1, C2, C3, C4, C5. what we do, each time we, this is 1 0 0 0 0. Similarly, this is 0 1 0 0 0. That one particular control bit is assigned 1. This is unencoded format. Now, if it is encoded one, we use a decoder. So, here if we, for 5 outputs, we need a 3 to 8 decoder. So, we need a 3 to 8 decoder. Here only 5 lines will be utilized, these 5 lines will be utilized and these 3 will be unutilized. So, here only 3 bits are necessary, 3 bits are necessary. Here it is a 5 bit. So, in this way encoded format provides a short control field and thus results short micro instruction. So, the implementation of encoded format is like that, only D0 D1 will be the input of decoder and the outputs will be that 2 will be the actual control signals, like in this example C0 C1, 1 is no operation. Actually, there are 3 operations. If we include the no operation itself is a no is one operation and one line is unused. So, this is unused. So, this is the implementation of encoded format using decoder. So, now we see that the different type of micro instruction. So, micro instructions are of 2 types. One is called the horizontal, another is vertical. Now, the horizontal micro instruction mechanism provides long micro instructions, a high degree of parallelism and little or no encoding. Whereas, the vertical micro instruction, it offers short micro instruction, it has limited parallelism, but it has considerable encoding. Now, we see the microprogramming. So, microprogramming is the technique of writing microprograms in a microprogrammed control unit. Writing microprogram is similar to writing assembly language programs. Microprograms are basically written in a symbolic language called micro assembly language. Now, these programs are translated by a microassembler to generate microcodes, which are then stored in the control memory. So, just like our concept of software, again these are also the instructions are nothing but software. So, these micro instructions are written in some language called the micro assembly language and they are translated by assembler, and then actually these programs are stored, or these micro codes are stored in control memory. Now, how they are implemented, how this control memory is implemented. In early days, the control memory was implemented using read only memories, ROMs. So, it cannot be changed. So, nowadays people have changed the type of memories, so that it can be more flexible or the program can be changed easily. So, now the control memories are realized by using some writable memories, not the read only memories. So, write is also possible. So, it provides the flexibility of interpreting different instruction set by rewriting the original microprogram, and this allows implementation of different control units using same hardware. Now, using this approach, one CPU can interpret the instruction set of other CPU. Now, the design of a microprogrammed control unit we consider, and the example we have taken is the same example of that hardware control unit. We have considered a 4 by 4 unsigned multiplication. So, this is 4 by 4 unsigned multiplication. The technique is the repetitive addition. So, here the as it is a memory, so there will be some address and some content. So, the control memory address, say we give the control memory address are 0, 1, 2, 3, 4, 5, as there are 6 micro instructions. And what will be the control words or the content of the memory? So, at 0th address, it will be 0th address that register R is reset to 0 and the register M gets the in bus, say the multiplicand. And see, these are two independent operations and they can be combined to get a parallelism. So, these are in 0th address. Now, address 1, the register Q gets the in bus, say the multiplier. So, Q gets the value of multiplier, whereas M is multiplicand. Now, address 2, the operations, the register R is R plus M, as it is a repeated addition. So, we have to check that how many additions are there, because I want Q number of additions, because Q is my multiplier. So, every time after each addition the multiplier is decremented by 1, that is Q is Q minus 1. At address 3, if z equal to 0, then go to loop. Address 4, if out bus, the register goes to out bus, that means this is the result, the product, and then address 5, the halt, go to halt means it is the program is completed. So, these are the control words stored in the control memory. So, the unsigned 4 by 4 multiplication uses repeated addition and the result is assumed to be 4 bits wide. Now, to implement this microprogram, the hardware organization of the control unit, we can think like that. See, what are the various components of this microprogram control unit or the microprogram multiplier control unit, unsigned multiplier. See, here it has one multiplexer, one microprogram counter, the control memory and the control word register. So, we see the different components. We see that different components. First is the control memory. This is the main component of the design and it stores the it contains the microprogram. So, the microprogram is stored here. Now, next one is the microprogram counter. It is called the MPC. It holds the address of the next micro instruction to be executed. Now, MPC is initially loaded from an external source to point to the starting address of the microprogram. The MPC is similar to program counter. So, MPC is incremented after each fetch. If a branch instruction is encountered, the MPC is loaded with the contents of the branch address field of the micro instruction. So, this is the function of a microprogram counter. In short, we can think that MPC is just like a PC, the program counter of the CPU. Now, the control word register or CWR. So, control word register, each control word in the control memory is assumed to contain 3 fields. One is condition select, branch address and control function. Each micro instruction fetched from the control memory is loaded into CWR, the control word register. Now, the organization of the CWR is same for each control word and contain the 3 fields, these 3 fields condition select, branch address and control function. And in the case of a conditional branch micro instruction, if the condition specified by the condition select field is true, the MPC is loaded with the branch address field of the CWR. Otherwise, the MPC is incremented to point to the next micro instruction. So, if the condition is satisfied, then this register will be loaded to the content of the branch address. Otherwise, it will be MPC is incremented just like PC to point to the next micro instructions to be executed. Now, the control function field contains the control signals. And another is the multiplexer, which selects one condition based on condition select field of CWR. So, input of multiplexer is the condition select fields. So, if we see the design now, so first is a multiplexer. So, it has 3 lines, the 0, ground line, 1, 2. This is actually the input Z and this is some VCC line. This is a 1 bit. So, this is a load or increment. Load or increment according to the value. Now, microprogram counter MPC and it has some reset line, because always for the first time it starts execution, this should be initialized, that means it should be a reset. This is my control memory. One size is given here 6 by 12. Later we will see that how actually the size of this control memory is determined. Now we are assuming one size. Now the control word register, as already I mentioned, it has 3 fields. See, this is condition select, branch address and control functions. So, if the if the condition specified by the condition select field is true, so this condition select field, if this is equal to this is 1. So, condition specified by condition select field, if this is equal to 1, then the content of this branch address is loaded to the MPC. So, this is the line, it goes to the MPC. Otherwise, MPC is incremented by 1 just like PC, and the control function field contains the control signals. So, here how many control signals are there? We have seen that control signals should be, say we are defining C0, C1, C2 up to C6. Now, see what are the control instructions, the control signals. So, these are the 7 control signals and we can write the control signal. C0 means say the reset, C1 is M is assigned to multiplicand, C2 is Q is assigned to multiplier, then the actual addition is in C3, then it is the decrement, multiplier decrement, then the result goes to out bus, that is activated by the control signal C5. So, we can write out bus is assigned to R, and then this is the completion, that R is F. So, these are the 7 control signals. So, we need 7 control signals. Now, what are the condition select field? Because just now we have seen that the control word registers have 3 fields: condition select, branch address and control functions. So, depending on the number of micro instructions or number of micro operations to be performed, the number of control signals to be determined, and that will directly gives the how many control signals will be generated by the control functions. in this particular example, there are C7, C0 to C6, these 7 control signals are generated from the control functions. So, we have to design our control functions of control function field of CWR, the control word register accordingly. Now, we see the condition select and branch address. So, the first we see the condition select. So, if there is 0 0 condition select fields are 2 fields if we take, then there is no branching, that means no condition. 0 1 branch if z equal to 0 and 1 0 means this is a unconditional branching. So, there are 3 situations. One is 1 0 means unconditional branching, means the no condition to be checked. So, always it will be a branch. 0 1 means a condition is there, that means branch if z equal to 0, this type of condition to be checked. 0 0 means no branching, is a sequential thing, it will not jump to anywhere. So, no branching is 0 0. So, as there are 3 interpretation means 3 operations are necessary. So, the condition select field is sufficient to have 2 bits only. So, we see what will be the size of control memory. See, size of a control word should be size of condition select field, size of branch address field and number of control signals. So, just now we have seen the number of control signals are 7 and size of condition select field, is 2. Now, there are 6 control memory address. See, just we have seen there are 6 control memory address 0 through 5 are required for the control memory to store the microprogram. Therefore, a 3-bit address is necessary for each micro instruction, as there are 5 address. So, we need 3-bit for encoding these addresses in binary. So, if we take the binary value, size of branch addresses is 3, as there are 6 control words, as there are 6 control words. So, for 6 memory addresses, control memory address is necessary, and for that we need a 3-bit. So, size of control word is the sum of these 3 fields. So, 2 the condition select, 3 the branch address and 7 the number of control signals. So, it will be 12. So, size of control memory is 6 bits by 12 bits, 6 bits by 12 bits, because the microprogram requires 6 addresses, 6 addresses and the control word is 12 bits wide. So, the memory size will be 6 by 12 bits. You can write this is 72 bits. So, this way the size of memory can be calculated. So, we have seen the size of control memory. Now, now we consider the micro program for the unsigned multiplication, the example we have considered. First we see the, actually we have to consider three things. What will be the ROM address, second is the control word, and for these two we will see what are the micro operations to be performed, and this gives me the micro program, because these are the set of micro instructions or micro programs that generates the micro program. So, mainly what will be the ROM address and the control word that we have to see. Now, ROM address, as there are 6 addresses. So, in decimal 0 to 5 and binary 000 001, because we need, as there are 6, we need 3 bits to encode. So, simply 3 bits are necessary for this ROM. Now, the control word. Control word has 3 fields: condition select, branch address, control function. Now, you see the condition select. Condition select, we have seen that we need only 2 bits for condition selects. Branch address is 3 bits, and the control functions are C0 to C6, means the 7 control functions. So, if the condition select is 00, say condition select, we consider the first one, condition select is 00, then the branch address is 000, and say control functions are both C0, C1, both C0, C1. C0 was a reset and C1 is the multiplicand is assigned to register M. As these two are parallel, so that is why both C0 and C1 together are 1. So, 2 1 in one row of the control function indicates a parallelism. That means, 2 micro instructions are combined, and this is the select line for that. Similarly, the condition select is 00, branch address is 00, because it is not going anywhere. Then C2 control signal is generated, means the C2 means the multiplier is assigned to register Q. Now, again condition select is 00, branch address 000. Now, again C3, C4. C3 means this is the addition, R is R plus M, and this is the C4 is Q equal to Q minus M. Again 2 micro instructions are grouped together, and this is the condition select, because no branching. Now, when condition select is 0 1, this is 0 1 0. So, control functions are all 0. because if z equal to 0, then it goes to address 2. Now, when select is 0 0, branch address is 0 0 0, then C5, and C5 means the register R is assigned to out bus, that is selected. If it is 1 0, then 1 0, branch address is 1 0 1, because go to address 5. So, this is a halt. So, this is a go to 5 instruction, go to 5, and this is a go to 2, go to 2. So, actually if we see the comments or what are micro instructions are being performed. So, these are the, if we take, these are the serial number or the decimal number of ROM address, we can tell these are the ROM address in decimal, ROM address in decimal. Then at 0th address, actually these two instructions C0 and C1. So, here C0 C1 are C0 C1 equal to 1, no branch. Here Q is in bus, that means C2 is 1, no branch. R is R plus M, Q is Q minus 1. So, again here it is here it is R is R plus M, Q is Q minus 1, and F is R, means the result. These are actually C3, C4, C3 R is R plus M is C3, C3, C4 and C5. Now, next is a, if z equal to 0, then go to 2, go to 2 means in decimal 0 1 0, and go to address 5, this is a unconditional 1 0 1. So, that is why here it is a branching to address 0 1 0, here it is a branching with address 1 0 1. So, if we check now, if we check this thing, then it is go to 2 and go to 5. That is why it is go to 2 and go to 5. This is go to 2 and go to 5. Now, we see the whether the length of micro instruction can be reduced. See, what we have seen, that it is obvious that the control function field contains all zeros in case of branch instructions. So, in case of branch instruction, these are the two branch instruction, one is go to 2 and go to 5. So, the branch address is 2 in decimal 5, and then these control functions or the control signals of the functions are 0. Now, in a typical microprogram, there may be several conditional and unconditional branch instructions. So, therefore, a lot of memory space inside the control unit. But now, what we have seen that if it is a branch instruction, then actually the control functions are control signals are zeros. Control functions generates 0 control signals. So, in practice the format of the control word is organized in a different manner to minimize the size. This reduces the implementation cost of control unit. Now, whenever there are several branch instructions, the micro instructions can be formatted by using a method called multiple micro instruction format. Now, in this approach the micro instructions are divided into two groups, operate and branch instructions. And operate instructions initiates one or more micro operations. It initiates one or more micro instructions. So, after the execution of operate instruction, MPC will be implemented by 1, and in case of a branch instruction, no micro operation will usually be initiated and the MPC may be loaded with a new value. Now, this means that the branch address field can be removed from the micro instruction format. So, the control function field is used to specify the branch address itself. So, now if we see the reduction, so this white marked column branch address that can be detached, that can be removed from the control word. So, now the size will be only the condition select and the control functions. So, reduction will be, now this select will be 0 0 0 1 1 1 1 0 and the operations are no branch for 0 0, branch if condition 1, branch if condition 2, because here there are only 2 branches, and this is an unconditional branch. This is an unconditional branch. So, complete, and this is go to 2 and go to 5 for this particular example, and always it will be 0 0 whenever there is a no branch. So, the old memory size was 72 bits because 6 bit address and 12 bits control words. Now, for after removing the branch address that it becomes 7 plus 2 9 bits, 7 control signals and 2 condition select fields. So, this is 7 plus 2 and new size will be 6 bits, the address remains same, and by 9 bits. So, these are 54 bits. So, this is the reduction of length of micro instruction. So, if we the modified one design, if we write, again this will be a multiplexer, the microprogram counter control memory is now becomes 6 into 9 instead of 6 into 6 by 12. So, the now this will be S0 S1 only the select lines and C0 to C6 the 7 control feeds, and there will be no branch, there will be no branch, and these are the C0 to C6 lines to the processing section. So, in this way the reduction can be possible for the microprogrammed memory, that design or length of micro instruction we can tell. Now, we see that quiz of this lecture. So, using these hardware components, say 4-bit general purpose register, 4-bit adder subtractor, tri-state buffer, design a control unit using microprogramming to perform the following operations. Now, we can use counters, decoders and PLS, and the operations are like this. If the 4-bit number in register B is odd, then 0 is assigned to outbus, otherwise outbus is A plus B by 2. A and B are 4-bit numbers, and we assume data is already loaded into B. So, this is the quiz of this particular lecture, and here we finish this class. Thank you. So, already we have read the design of a CPU, mainly the two parts we have read, the design of ALU and the design of control unit. There are two approaches, the hardware control unit and the microprogrammed control unit. Now, this class will read a design of a microprogrammed CPU. So, now first we assume the programming model of the CPU. The CPU that we want to design contains two registers, an 8-bit register A 2-bit flag register F. The flag register holds only 0 and carry C flags. All programs and data are stored in a memory, and the memory size is a 256 by 8-bit RAM. Now, first we see the hardware schematic of the data flow part of this processor. So, it has the program counter, PC, MAR the memory address register,